Bam! Mr. True. In this video, we're going to learn how to solve a new or a second type of differential equations. Up until now, we've only looked at differential equations, which is simply just an equation with a derivative in it. And we've solved it using the process of separating the variables, maybe having all the factors of x to the left-hand side, all the factors or functions in terms of y on the right-hand side, and then integrating both sides of the equation. Well, if we look at this here, we can maybe take this term of 3 over x times y, move it to the right-hand side, and if we then try and say, well, move this dx over to the right-hand side and then bring the factor of y over to the left-hand side, well, even if we divide both sides by y, it may get that factor of y out of the second term, but it's going to make this 1 over x cubed times y. So we're not able to separate these variables. We're not able to solve this differential equation, at least not with the techniques we've learned so far. Well, we're going to find that general solution. We're going to see that we have a derivative sort of to that first power, or not a second or third derivative, but a first order differential equation. We have a y prime, we have a y, and we have here basically a coefficient of 1, a coefficient of 3 over x multiplied to this factor of y, and then we have a 1 over x cubed. Well, that means that we're looking at a linear equation in the form of a of x times dy dx plus b of x times y is equal to c of x, where both the function y, or y of x, we're going to be looking at functions where basically the independent variable is x, and its derivative y prime are all multiplied only by functions of x. And how do we solve this? If we cannot separate the variables, how do we solve it? Well, this is actually our first example, is kind of a special case. It's actually an exact, or we'll be very quickly putting it to an exact form, first order differential equation. And then we're going to take a look at some notes where I show you how to come up with an integration factor and have the systematic process where when you have these types of differential equations, you can, not too terribly difficult, but put it into a form that allows you to just solve it with integration. And here we're going to, and you won't necessarily see this yet, but I'm going to help us along here. We're going to multiply both sides of this equation by x cubed. Now, I'm going to show you systematically how you come up with a good integration factor, but for here, because I know where we're leading, we're going to have x cubed dy dx plus what? We have x cubed times 3 over x is going to give us a plus 3x squared y, and then that's going to be equal to x cubed divided by x cubed is just simply equal to 1. Well, this is still a differential equation where we're not going to be able to separate these variables and use techniques that we know up until this point. But if you look at the left-hand side of this equation long enough, you might recognize a pattern. We have an x cubed here, which I'll just temporarily call u. We have plus, I wrote plus twice. We have the sum of two terms, and we have an x cubed and 3x squared. Actually, 3x squared is the derivative of x cubed, so we're going to let's call that u prime. We have a y, and we have a y prime, or dy dx, a derivative with respect to x. So we basically have, let's see here, u v prime plus u prime v. Do you recognize what's going on over here on the left-hand side? This is the result of taking the derivative using the product rule. So I can actually rewrite this left-hand side instead of u v prime plus u prime v as the derivative with respect to x of u, which we have here as x cubed, times v, which is y, and that's equal to 1. The left-hand side, it's the left-hand side of this equation, this differential equation, is the derivative of a product, and the right-hand side is just got a constant of 1. This is now very easily solved, so that we can get rid of the derivative in the differential equation. Let's go ahead and integrate both sides of this, and we're going to be integrating with respect to x. And, well, of course, the integral of a derivative, those are inverse math operations, so this is going to just cancel each other out. It's almost like the dx and the dx cancel out, and the derivative and integral process also cancel themselves out, and we have x cubed times y is equal to, well, the integral of 1 with respect to x is just x, and because we're doing indefinite integration, don't forget your constant of integration. And we don't have enough information given here to help us find the particular solution. That's why the question is simply asking for a general solution to this differential equation. So this is the first time my students, and possibly you, we now know a way of solving a differential equation where we cannot separate the variables. But how do we create or transform a linear differential equation into basically an exact form that allows us to just simply finish the solving process through integration? Well, that's coming up right now. Finding an integration factor. Now that I kind of already told you that you want one side, now I'm going to have them set up so it's generally the left, to develop into the derivative that you get from the product rule. You might have been able to look at that first example and realize that, hey, if I just multiply both sides by x cubed, I'm going to create that u v prime plus u prime v pattern to finish that up. But it's not always that simple. So given the differential equation dy dx plus p of x, y, times q of x, the function I of x, I for integration factor, is equal to e raised to the indefinite integral of p of x dx. That's an integrating factor that transforms your linear differential equation into an exact differential equation, and ultimately giving you this idea that we have the derivative with respect to x of a product of two factors is equal to the right-hand side, which in this case is a formula, is e raised to the indefinite integral of p of x dx times q of x. Basically what you want, and it's kind of hidden in the way this theorem is written, is you kind of want to make, you do want to make a p prime show up in front of this derivative notation. So you have that product rule completed, the pattern of that. This is kind of like mumbo jumbo maybe at first, so we're going to walk through actually two examples. But our first one here, we have dy dx plus 2x plus 3 times y is equal to e raised to the negative x squared. Okay, so we have a derivative of the first order. We have a first derivative here, and we have a coefficient basically of 1. Our function y, since this is a y prime, has a coefficient of some function of x, 2x plus 3, and then we have another function in terms of x on the right-hand side. So, recognizing that we have a first order linear differential equation that is not solvable, we can't use separation of variables to solve this, and we're only going to have two tools in our toolbox. Okay, anyway, let's go ahead and set up that integration factor. So we have I of x is equal to e raised to the indefinite integral, and your p of x is the coefficient of your function y, or your coefficient of y. So our p of x here is going to be 2x plus 3. So we have e raised to the indefinite integral of 2x plus 3 with respect to x. Now, we're still going to have a base e, but we know the integral of 2x plus 3 is just going to be what? X squared plus 3x. So I is equal to e raised to x squared plus the 3x power. Now that integration factor is going to get multiplied to both sides of this equation. Okay, so I've put the parentheses around the left-hand side, distribute it here, and we have what looks pretty nasty. But remember, what we need to show up on the left-hand side here is the product rule. Do we have a sort of, let this be a u, do we have a u prime? Do we have a derivative of e to the x squared plus 3x? Well, the derivative of e to the u is e to the u times u prime, And, well, the derivative of x squared plus 3x is 2x plus 3. So here is our u prime. And of course, if we have y set up to be our v, then dy dx is our v prime. So yes, indeed, on the left-hand side, we do have basically the right-hand side, the result of taking the derivative using the product rule. So the left-hand side is, or it can be written as, get my yellow chalk, the derivative with respect to x of u times v, u e to the x squared plus 3x times v, which is just simply equal to y. And on the right-hand side, we have e raised to x squared plus 3x times e raised to the negative x squared. But of course, the right-hand side is the multiplication of two factors with the like or similar, not similar, but the exact same base. And of course, when you multiply like bases, you add the exponents. So we have e raised to x squared plus 3x minus x squared. Of course, those x squares are going to cancel out, giving us just simply e to the 3x. And now the left-hand side is going to be just the derivative of these two factors, but we're going to integrate, which is an inverse math operation, to that derivative. So we have the integral of the derivative with respect to x of e to the x squared plus 3x times y. And just to really get this notation beat it to death, we are integrating with respect to x. Those dx's are going to cancel out. The derivative and the integral basically cancel out. And actually, my textbook does not include this dx here. They just write an integral, but it bothers me having that there without the extra dx like you really, I believe, should. And over here we have e to the 3x dx. Okay. So the left-hand side, the derivative and the integral, those inverse math operations are just simply canceling out, giving us e to the x squared plus 3x times y. And on the right-hand side, well, and I'm running out of room, so I'm going to complete the chain rule pattern. The integral of e to the u prime is just e to the u. So we need to create or complete the chain rule pattern over here to allow us to integrate. Of course, we know that if u is 3x, then u prime is 3. We need that e to the u prime. And if we introduce a multiplication or a factor of 3, we need to balance that with a division of 3. And I understand I'm going through all this. If your teacher's been doing the completion of the chain rule over and over again, this is probably unnecessary for you to hear, but depending on your teachers, like for a lot of my school year, I teach with a straight u substitution. So my kids may not be used to yet, they should be, but may not be used to that process. So u prime, introduce a multiplication of 3, we need to balance that with a division of 3. Now, of course, we know that we're not really done when we're solving differential equations. We're never really considered done until we have it solved for y. So we're going to multiply each of these three terms by e to the x squared plus 3x power, which is going to give us y is equal to 1, or let's just write this as e to the 3x power over 3e to the x squared plus 3x power. And then that is plus c over e to the x squared plus 3x power. When you divide like bases, of course, you subtract those exponents. I'm going to clean this up a little bit. And 3x minus x squared plus 3x. The 3x's, of course, are going to cancel out. And we're going to have a final answer here of y is equal to, and we have, again, e to the 3x minus x squared minus 3x. So I'm going to write that e to the negative, well, I'm going to write that as e to the negative x squared power. So you have 1/3, y is equal to 1/3 e to the negative x squared pattern plus c. And thinking about, I'm going to just write this as a, well, without a fraction. We're going to let that e, that base e, come up to the numerator of our second term by multiplying or changing the sign, right? Multiplying the exponent by -1. So we have c times e to the negative, got my arrow out of in the way. E to the negative x squared minus 3x. And this is our general solution to this first order linear differential equation. Example 3 coming up right now. Bam! Last example. We have the question here asking us to find the general solution to this differential equation, dy dx over minus sine of x is equal to 2y. Again, certainly an equation that we cannot solve using separation of variables. Okay, so how are we going to tackle this problem? Well, again, we have a coefficient of 1. And, oh, well, this isn't exactly matching up with the way I wrote out that sort of that first order differential equation formula earlier in our notes. So we'll just move this around a little bit. Move the sine of x over to the right and the 2y to the left. And now recognizing that in front of our dy dx we have a coefficient of 1. In front of our function y we have another coefficient of negative 2. And we have our sine of x on the right-hand side. So really we have sort of functions in terms of x, if you will, even though they're just constants, in front of our dy dx, or y prime, and y with another function in terms of x on the right-hand side. Let's find that integration factor, that integrating factor. So we're going to say that I of x is equal to, well, our p of x, at least in matching the notes in the way my book writes this out that I'm being consistent with. Our p of x is the coefficient of our function y. And the sine of x, just for good notes, is our q of x. So I of x is going to be equal to, our integrating factor is going to be equal to e raised to the indefinite integral of our coefficient of y, so negative 2 dx. And now integrating this, we have our integrating factor is going to be equal to e to the negative 2x. Now, I forgot to mention it earlier in the video, so I'll probably have already put a footnote in the editing, but again, we don't put a plus c here. We just generally assume that plus c, the constant, for our integrating factor to be equal to 0. That's why you're not seeing me write a plus c here. Now that e to the 2x is going to get multiplied to both sides of this equation, and we have e to the negative 2x dy dx minus 2 times e to the negative 2x y is equal to e to the negative 2x sine of x. Double checking that we do and have successfully created that product rule derivative pattern on the left-hand side, recognizing that we have a u here as e to the negative 2x. We have a u prime in the second factor. And if I write this as a plus negative, which I really kind of hate doing, we do actually have our u prime here. The derivative of e to the u is e to the u prime. The derivative of e to the u is, okay, so then we have our y and our y prime, and certainly that is that pattern that we have and use for taking the derivative of the product of two factors. So just cleaning up the left-hand side, writing it as a derivative with respect to x of those two factors, e to the negative 2x times y. And we have that e to the negative 2x sine of x on the right. Okay, well now we've taken our linear differential equation, used our systematic process now to write an exact form, an exact linear differential equation, wrote the left-hand side as a derivative for that product, integrate both sides, and let's just go ahead and for good measure again, because it bugs me not to, include our d of x. We're integrating with respect to x. The derivative and integration process or inverse math operations, e to the negative 2xy is equal to, and now we're in a little bit of a sticky situation here. I just want to make sure that my students and you out there, I don't know how much experience, you should have plenty if you're doing this topic in calculus, but make sure you remember that, that integration by parts. Of course, if you're integrating and you recognize that you have like your integral of the factor of two functions, the integral of u dv is equal to uv minus the integral of v du. This is going to require integration by parts. And for determining what you're going to set equal to u, you may know that LIATE acronym, which tells you that if you need some help identifying what part of this integrand to let be u and dv, well, it's often best to just look at this and go, okay, what factor in this integrand is the most complicated factor which easily integrates, or the LIATE rule helps you identify what factor in this integrand is going to become simpler as you take its derivative. And that normally in step one, and there's other acronyms that textbooks use, but mine will say, you know, is there a factor which is a logarithm? Is there a factor which is an inverse trig function, or just simply an algebraic expression, or a trig function, or maybe just an exponential function, and kind of go down the list. Okay, one, no, check here, no, check here, no, and so on and so on. So our sticky situation here is that neither factor becomes simpler when you take its derivative, nor when you integrate. And of course, integrating either one of those factors, sine of x or e to the negative 2x, is actually pretty simple. So this is going to require tabular method, and which is just a shortcut and a shorthand process basically for doing integration by parts. It requires multiple steps of integration by parts. And we're going to let dv, or u, we're going to let u be equal to e to the negative 2x, and we're going to let dv be equal to the sine of x. So we're trying to, in this tabular method shortcut sort of shorthand process, go through the multiple steps of integration by parts that we need. If the u were a simple algebraic expression or even a logarithm, there's lots of functions basically that as you take a derivative you get a simpler and simpler answer. A lot of times this u column, when you're doing the tabular method, will just go down to 0, and that's what tells you to stop your multiple steps of integration by part, or tells you when to stop that tabular method table. Here, if this is u, and we're going to set this up as and we're going to keep the sign of this when we do the product, u prime is going to be negative 2 times e to the negative 2x, because of course the derivative of negative 2x is negative 2. A derivative again, the derivative of negative 2x is negative 2, giving us 4e to the negative 2x. And I'm writing a little plus minus plus factor out here, because ultimately we're going to take what we write in our u column and ultimately our v column and multiply those together, right, for that uv minus v du. So if this is dv, we're going to integrate both sides and say that v then is equal to the integral of sine of x is negative, well, with respect to x, negative cosine of x. Integrating that again, we get negative sine of x. And I can just keep these columns going forever, but it's kind of hard to tell where to stop because the u column never becomes 0. But when you recognize that start to happen, this column, as you do the integration, and you can flip-flop these two. Actually, I could let u be sine of x and dv be e to the negative 2x, just because of the way this problem works out. But here we have a matching trig function. The sine of x showed up again. This is where we're going to stop and start going and then go from our tabular table to what we have as the integral of this expression. So we have the indefinite integral of e to the negative 2x sine of x dx is equal to, and I may have to stop the video and, okay, so anyway, almost done, thank you. We have e to the negative 2x times sine of dx is equal to, multiplying these together, we have e to the negative 2x times the cosine of x. Now this is negative times positive, and we're going to keep that sign the same. So this is actually going to be equals to negative e to the negative 2x cosine of x. Now we have another UV product here. We have negative 2 e to the negative 2x times negative sine of x. Negative times negative is positive. But here we're going to change the sign of this of this term. So we have negative times negative is positive, but it's going to be negative 2e to the negative 2x sine of x. Now, because our tabular method does not result in our u column becoming 0, basically telling us when to stop, what that means is that we're not actually going to have like our final answer, if you will. We're going to then need to stop here after that trig function repeated itself, go straight across now instead of angling down as we make these UV products, and just recognize that now what we're setting up is another indefinite integral. And we have positive 4 e to the negative 2x times negative sine of x, and we're keeping that sign. So we have, well, I wrote plus, but really it's going to be negative because we're keeping that sign, so plus a negative or minus 4, and I'm just bringing that 4 out, that coefficient 4e to the negative 2x sine of x dx. And I don't have a plus c written in yet because we have an indefinite integral written on both sides of this equation, so we're kind of still basically okay. I'm now going to move this term over to the left-hand side, with addition. So we have 5 times the indefinite integral of e to the negative 2x sine of x dx is equal to negative e to the negative 2x cosine of x minus 2e to the negative 2x sine of x. And now we just have that one indefinite integral on the left-hand side. We need to recognize and remember that integration, that constant of integration, so we have our plus c. Well, we're looking for solving and working out this e to the negative 2xy times y is equal to this indefinite integral. So we're going to divide each of these terms by 5 and do substitution because I'm running out of board space. So dividing everything by 5, we have e to the negative 2xy is equal to, and with substitution here, we have negative 1/5 e to the negative 2x cosine of x and negative 2/5, so minus 2/5 e to the negative 2x power times the sine of x plus c. Now, again, solving these differential equations, you never consider yourself completely done until you've solved for y. So we're going to divide every one of these terms by a e to the negative 2x, and we have y is equal to, well, e to the negative 2x divided by e to the negative 2x is going to be just 1, so we're looking at negative 1/5. Y is equal to negative 1/5 cosine of x. Again, for our second term here, that e to the negative 2x is going to cancel out again, so minus 2/5 sine of x plus c. And remember, we're dividing by e to the negative 2x. So we're looking at basically c over e to the negative 2x, which makes it, of course, plus c, bringing this up times e to the 2x power. And that is our general solution to, well, this linear differential equation. I'm Mr. True. Bam! Go do your homework.